Hello, I'm going to present reinforcement learning-based auto-router considering signal integrity. And my name is Min-Soo Kim. I'm master candidate of KAIST. My current research interest includes machine learning-based signal integrity and learning-based algorithm design of auto-routing. And this is my co-authors and colleagues. And Professor Jung Kim is my PI. And let's see the contents. Introduction and proposal of method and verification part and conclusion. Recent technology trends requires terabyte per second bandwidth. To meet this demand, data rate is increasing dramatically. Routing of this kind of high-speed channel highly affects to signal integrity. Therefore, an auto-router considering signal integrity is required. Then, let's see the detailed process of routing. There are two stages in routing: router planning and detailed routing. In this research, we focus on this detailed routing. In detailed routing, finding short paths is important because it affects to insertion loss, and reducing congestion is important because it affects to crosstalk. Finally, reducing number of layer changing is very important because it affects via transition effect and routing feasibility of another layer. So we have to minimize the number of layer changing. Connecting two pins with these multiple constraints is NP-complete, which means very complex. Reinforcement learning-based method can be one of the promising solutions for this complex problem. Let's see the reason of this. Several algorithms can be used to solve detailed routing. Maze router is widely used algorithm. It guarantees to find shortest path, but do not consider crosstalk and layer changing. The interesting candidate approach is meta-heuristic based algorithm, such as genetic algorithm or ant colony algorithm. These kind of searching methods are widely used for solving combinatorial optimization problem. However, for detailed routing, learning-based method is more suitable to compare with meta-heuristics. Let's see the why. That's because learning-based methods require only one iteration to obtain solution, while meta-heuristics need multiple iterations to obtain solution. Main scheme of meta-heuristics and learning-based approach is very similar. Main difference is that learning-based approach make trained model, but meta-heuristic approach make the one solution, not a model. Let's see specific comparison of various algorithms. First, exact algorithm guarantee optimal solution, but it is NP completeness, so impossible to use. Then we must use approximated solutions algorithms. In this research, we compared these heuristics and learning-based method in terms of optimality. Because main hardware usage, heuristic use CPU and learning-based method use GPU, it is difficult to find fair setting to measure speed. That's because we provide time complexity analysis. As I said before, time complexity between meta-heuristic and learning-based method is faster than meta-heuristics because of this. Then let's compare with time complexity of heuristics and learning-based method. Time complexity of heuristic is linear time. It is fast. But time complexity of learning-based method is n squared if we use transformer as neural network model. If we use linear transformer as neural network model, we can reduce time complexity to n. That is, same time complexity. But learning-based model use GPU, which is very parallelizable. Then, in practical point of view, maybe the learning-based model is faster. But we didn't experiment at all. The main fact that I want to say for this is the flexibility of the learning-based model. Changing neural network model from transformer to linear transformer is not that difficult things, which means we can improve the learning-based model every year, every single year. So also, if problem setting is slightly changed, we can retrain the model with new evaluation function. But if some problem setting is changed, in heuristic point of view, this heuristic have to redesigned entirely. So it has low flexibility. So this is merit of learning-based model. It is improbable. It is flexible. So this is why we designed learning-based model. Therefore, we propose reinforcement-based auto-router considering signal integrity, and we call it as AI router. This is whole picture of learning AI router. Let's see one by one. This is detail of encoder network, and encoder network is almost same as the transformer network proposed in Attention is All You Need and Attention Run to Solve Routing Problems. It embeds input node from hidden nodes. So the detailed explanation of this multi-head attention and feed-forward is omitted, and detail of this is provided in Attention is All You Need paper, which is first proposed paper that introduced the transformer architecture. The novel design of this in this research is decoder. And then let's see specific of decoder. In decoding processes, it sequentially makes the path from the source pin as it makes next node 4, next node 5, 10, and target pin. How to from this embedded hidden node and context embedding, the multi-head attention refer these holdings and makes action. Then let's see the details of context embedding. In context embedding vector, this is consists of 6 kind of hidden vectors. The average of whole hidden vectors and obstacle vectors, crosstalk vectors, loosely crosstalk vectors, and previous node and target pins. So it care about this crosstalk red region and loosely crosstalk blue region and obstacles and destination and previous pin, and then check all these processes and determine next node. Then let's see how loss function is made. The input vector expressed in grid space like this, and each grid point is represented by 6-dimensional vector, which contains 3D point position vector x, y, z, and various penalties. We set 2 crosstalk penalties. This red region is 1 W crosstalk region, which means if the signal to signal width is W, then if the space is W, then we call it one W crosstalk regions, and this red region. And if the space is larger than 1W but shorter than 2W, then we call it loosely crosstalk region. And we made the two level of crosstalk region, and this gamma is via transition penalty or layer changing penalty. So the whole loss function evaluated like this. So this is crosstalk penalty, loosely crosstalk penalty. This is Euclidean length, which means wire length, and this gamma means via transition penalty. So this L function contains all kind of penalties. Then after that, the calculated loss become the value, and the parameter theta, this is from encoder decoder models, neural network models parameters theta. So these constructs whole policies. So final objective function J can be expressed as follows: expectation of loss function. Then we can optimize, our final goal is minimizing this objective function, which means minimizing these penalties. Find the theta that minimize these penalties. That is our final goal. Then we can make gradient of this objective function. It is, we call it policy gradient because there are gradient of log policy. We call it another name that capital rainforest, and this is rollout baseline. It is scaled to reduce whole variance. Details of reinforcement learning algorithm will skip. Just the way to finding this theta star, the optimized AI router. This theta star minimized this J, these penalties, which means this theta star can find optimal routing path. And let's see the experimental result. This is our experimental setting. This is number of training set, validation set, number of nodes, number of signal layer. Optimizer is, we use Adam optimizer, and learning rate and training epochs. So this is training data. As training loss converges, validation loss also converges. So we can say there are no overfitting. It is very stably converged, well trained. And let's compare with other heuristics, Ree algorithm and A-star algorithm. As you can see this, Ree algorithm choose the upper region. There is many crosstalk regions are here. A-star algorithm also choose upper region. So many crosstalk region here. That's because these heuristics cannot determine the crosstalk region and uncrosstalk region or something, but AI router can decide where crosstalk region and uncrosstalk region, and how to solve this routing problem as shorter wire lengths with no crosstalk. So it optimized these two parameters. So we can say that our AI router outperformed previous heuristics. And let's see this multi-layer routing experiment. Previous major routers cannot perform multi-layer routing, but our AI router can perform multi-layer routing. The question is, what is optimal BR location, and what is optimal number of BR to use? There is signal one block the path, so we have to use 2 BR, and this BR location is very nice. So there is no crosstalk region, and wire length is very short. It is very optimal. So AI router successfully performed the 3D routing. As a result, we propose RL-based AI router. Our AI router outperforms conventional major routers in terms of SI in specific test case, and proposed algorithm can be further applied to various application targets by just fine-tuning the objective function of RL. Thank you for listening.